In this section, 16.7, we're going to be looking at surface integrals, and we actually set up the apparatus for this back in 15.5. So just for a quick refresher, the idea is that we have a parametrized surface. So we have a little patch of R2 over here, and we're going to take it and map it into R3 by sigma. And sigma is going to do something, distort it, map it around, and make it into some kind of like crazy warped surface. All right, so the mapping goes from R2, 2 inputs, to R3, 3 outputs, and we can find the area of this little parallelogram spanned by the partial derivatives by taking the cross product, so that's given here. The area element, so the density of area for this, is going to be the length of the cross product times the dA, which will be set up as like du dv or dv du or something like that. And back in section 15.5, we computed the area of this surface by just taking the double integral of this area element. So in other words, this integral right here in the parameter domain. Okay, so all we're going to do right now, get ready for this, it's going to be so exciting, is we're going to give it a scalar integrand. So the idea is that if we have the double integral over s of f ds, this is going to be the double integral over the parameter domain of f of sigma uv, meaning that we substitute in the formulas that we selected back here for our x, y, and z in the arguments of f, times sigma u cross sigma v, absolute value dA, right? So there's nothing really new or exciting going on here. Let's look at a couple quick examples. So suppose we take f to be x squared, and s is going to be the unit sphere. And so I took this one because, hey, we already know how to parameterize the unit sphere. We use spherical coordinates. So we're going to have x is going to be sine phi cosine theta, y is going to be sine phi sine theta, and z is going to be cosine phi. And this is the unit sphere, so the radius is fixed equal to 1. So the way that it is different from the usual spherical coordinates is that there's no rho. Rho is just fixed equal to 1 all the way through here, so it doesn't even really show up. And then just like in spherical coordinates, if we look at sigma phi cross sigma theta, we're going to get sine phi. The rho squared also does not show up, of course. Okay, so then we have the double integral of x squared ds over this surface, and it's going to be, let's see, so we need theta running from 0 to 2 pi, and we need phi running from 0 to pi to go all over the sphere exactly once. And then we've got our integrand, so x is given by sine phi cosine theta, so when we square it we get sine phi squared cosine squared theta. And then we've got our Jacobian, which we just said was sine of phi, and then that's d phi d theta. So I can combine this guy with the other ones just by making that into a 3. And let's see, now it looks like we can fubinate. Check it out. We've got a product of phi times a product of theta, and all of our bounds are numerical constants. So we can do 0 to 2 pi cosine squared theta d theta times 0 to pi, I love this shortcut, sine cubed phi d phi. And these are both fairly straightforward. Boils down, you get 4 pi over 3 as your answer. Okay, so there's one example. We can do another example. So the other thing we learned how to, the other kind of surface we learned how to parameterize easily was when it's the graph of a function. So suppose we want to integrate y over the graph of take f to be x plus y squared. And we'll take our range to be, our domain to be 0 to 1 for x and 0 to 2 for y. All right, so let's see what's going on now. Okay, so our parametrization, we'll just use x and y for our variables, and it's going to be x and y and f of x, y. That's going to give us our surface parametrization. So we just need to look at the partials of f to work this out. So we've got df dx is 1 and df dy is 2y. So when we look at the square root of 1 plus fx squared plus fy squared, we get 1 plus 1 squared plus 4y squared, which is root 2 times 1 plus 2y squared. There we go. Okay, so that's the part we need for our surface area element. So our integral, we are looking at the double integral over s of the function y with respect to ds. And so this is over the parameter domain d, we've got, let's see, 0 to 1 and then 0 to 2. So I'm doing the dy integration first. And we've got our integrand of y. And then we've got our area element root 2 root 1 plus, oh, how did I, oh yeah, that's right, plus 2y squared. Yes, okay. And so that's, we're doing dy first and then dx because we want the y's to match with 0 to 2 and the x to match with 0 to 1. Okay, and at this point, it's more or less straightforward and ready to go, yeah? So let's see. So we can pull out the constant root 2, and then I guess we can Fubinate again. So we've got a product of, sorry, the integrand only depends on y, so we can yank out the 0 to 1 dx, and then we've just got 0 to 2, and I've got 1 plus 2y squared in the square root, and then a y dy. And so if I take this stuff in the parentheses for my u, then I'll have right here, I'll have my du, maybe with a constant, and that's gonna give me, let's see, I'll have a root 2 and then a 1 from the first integral, and then a 1/4 times the integral from, let's see, 1 to 9 u to the 1/2 du. So what I did there is I did my u equals 1 plus 2y squared, du is equal to 4y, and then put the 1/4 over here, and that's where this comes from. And then of course change the bounds. So that gives, let's see, so we've got root 2 over 4, and then the other guy is going to become, let's see, so 1/2, that's going to become 3/2, and so we'll have to multiply by 2/3 out in front, and then we'll have u to the 3/2, 1 to 9, and something somewhere cancels. What do we have? We've got, that cancels and leaves a 2, so we've got root 2 over 6 times, and then we're going to get blarg, I guess, what, 27 minus 1. Okay, so that's 26. That's got a factor of 2 in it, so we can simplify, and what do we get? So root 2 over 3 times 13. 13 root 3, yeah, there we go.